So we are going to talk about a concept called magnetic flux, which is the cornerstone of understanding how much current is generated by a loop of wire in a magnetic field. And the formula for magnetic flux is B for magnetic field times A for area times the cosine of the angle between them. Now you may be asking yourself, how can there be an angle between a magnetic field and an area? I'm going to go back up to our scenarios here. Remember, in this scenario, I've cleaned up my artwork a little bit here. In this scenario, I've got a loop of wire. And by the way, I have it empty on the right-hand side, but this loop of wire is connected to something, some kind of resistor. Ooh, let me make that a bit skinnier. So ultimately, where we're going with this, come on, Notability, where we're going with this is that we're going to get a current to go through this resistor. Maybe this resistor is a light bulb. Maybe it's, it could be any kind of appliance. But in my pictures, I'm not including the resistor. I'm just focusing on the loop of wire for now because I'm focusing on the flux. Anyway, I talked about how if you take this loop and pull it in and out of the magnetic field, that changes the flux. And it changes the flux because here, in scenario 1, the magnetic field is whatever the magnetic field is. I would give you a value. And the area is the area of the circle, the area of this full loop, and we certainly could compute that. And then this area would change as a function of time. So let's see if this will still work for me. So if I were to, my magnetic field is coming with me. But if you can imagine me pulling the loop out of there, so if I take that loop and pull it out here, the effective area is 0. So I still have my magnetic field, but my effective area is 0. And so we would say that the flux has changed because the amount of magnetic field going through the loop has decreased. Okay, here it is shown from a side view, or my attempt at drawing a side view. So the loop could go in and come out of the magnetic field. We'll put it back in the magnetic field. The wire itself creates this area, and there is a vector associated with the area. The vector associated with the area is perpendicular to the plane. So the area vector would look like that. And the magnetic field vector I've already drawn. So in this case, the angle between B and A is 0 degrees. And in our formula for flux, you're going to see the cosine of the angle. The cosine of 0 is 1. So this scenario is going to maximize flux. Okay, let's come down to this scenario. Here we've got the cross-sectional area of a square loop of wire. Okay, the area vector in this case is perpendicular to the magnetic field vector, right? Because my magnetic field vectors are to the right. So this angle is a 90-degree angle. So the cosine of 90 degrees is 0. So this scenario is going to minimize the flux. Evidently, I can't spell the word minimize today. And as this thing rotates, it should not be a surprise to you that it creates a sinusoidal function or a cosinusoidal function, and the current and the voltage are going to change accordingly. Okay, so I have a better picture of that last scenario down here. There are some videos that we'll watch in class with generators that we'll talk more about the slip rings and the carbon brushes and so forth. But what you need to know is that we have an external magnetic field. So in order for this to work, you need an external magnet, you need a loop of wire, and you need to turn that loop. And well, that's one way to do it, actually. So back up here that we saw 2 other ways to do it, and we'll see that in some examples coming up. What happens to the flux of coil as it rotates in a magnetic field? In this scenario, if it starts this way, the flux increases. The flux through the coil in this picture is 0. And what must we do to the wire loop to change the flux? We must rotate it. Okay, so now what we're going to do is we're going to look at what happens when we change that flux as a function of time. And one thing that we always want to keep track of is this question: is the flux increasing or decreasing? Okay, so here's what happens when we change magnetic flux as a function of time. What happens is we induce a current and an EMF, which is another word for voltage. So in this formula, we've got EMF or voltage equals the opposite of the change in flux over the change in time. Remember that flux is BA cosine theta. In the cases that I've shown you so far, what's changing is the cross-sectional area. So the change in flux would be B times the change in area times the cosine of the angle. If indeed that area is changing. So, for example, in this situation where we change flux, in this situation where we change flux by moving this bar, we're changing the angle, but not, we're changing the area, but not the angle, okay? In this situation, we're changing, here, when I was pulling this in and out of the field, we're changing the area, but not the angle. In this situation, we're changing the angle as this thing rotates, but not the area. So we'll have to think about the scenario as we move forward there. Let's see, a couple of things to remember, a couple more things, that B is magnetic field strength. We've been using this now for a while, and it's measured in Tesla. And area is, or A is area, and it's in square meters. If I take the formula for flux, or for change in flux, and make a substitution, then I can rewrite this to be that the EMF or the voltage will be negative B times change in area times the cosine of the angle. Again, this is assuming that we have a scenario where the angle is the area is changing and not the angle, over change in time. Okay, let's go back to this scenario where I'm going to induce a current. I better get my magnetic field back in there. Okay, so I'm going to move this bar, and by moving this bar, I'm getting a change in area, and that change in area changes the flux and therefore induces an EMF and a current. So one thing to realize is that if I drag this bar at a velocity v, that the change in area over the change in time is going to equal length times change in width over change in time, which is going to equal length times velocity. So in this scenario, there's L, there's W, dragging the bar. As we drag the bar, this cross-sectional area increases as a function of time, and delta A over delta T is going to equal L times V. So that is this portion of the formula. So I could rewrite this formula as E equals negative B L V times the cosine of the angle. Now in this scenario, the angle is 0 degrees, so the cosine is 1. And I'll talk about what that negative sign means in a moment. Okay, so I've got the formula here on the next page. The EMF induced in a length of wire moving through an electric field. I'm sorry, this is not right. Not electric field. Hello. Magnetic field. Is given by EMF equals BLV. Okay, so let's see if we can figure this out. I didn't really give myself a ton of space, did I? I'm going to copy this, put it on a different page. Okay, that's better. Okay, an external magnetic field of 5 Tesla is pointing out of the page. A U-shaped wire is in the plane of the page, perpendicular to the B field. A resistor of 10 ohms is placed at the ends of the U-shaped wire so it creates a closed loop. Draw a diagram of the situation. Okay, so I'll start with my external magnetic field. It's pointing out of the page, so I'm going to make dots. And it's a uniform field, so I'm trying to space them as evenly as I can. Indicate that that is a uniform field. Okay, that ought to do it. Let's see, and then we've got a U-shaped wire in the plane of the page. So like that. And then we've got a resistor. So that's going to look like this. And again, the idea is that I can drag this resistor back and forth to induce a current in that loop of wire. Okay, so let's see. I've got a B field, 5 Tesla. My resistor is 10 ohms. I drew my diagram. Okay. It says that the wire is 5 centimeters long and is moved across the U-shaped wire at a speed of 3 centimeters per second. Calculate the induced voltage. Okay. So the length of this wire here is 5 centimeters or 0.05 meters. And the velocity of it is 3 centimeters per second or 0.03 meters per second. So the EMF or voltage is just going to be VLV, which is going to be 5 times 0.05 times 0.03, and that is 0.0075 volts. Okay, now I'm going to add a couple of bonus questions. You love bonus questions, don't you? Bonus question 1. This one should be pretty straightforward. Find the current. So, first of all, we have this loop of this closed loop, okay? And we have a resistor, and we know what it is. So we've got that the voltage or EMF is 0.0075. We've got that the resistance is 10 ohms. So I just need to use Ohm's law to find the current. Okay, that worked pretty well. Here we go, bonus number 2. Which way does the current go? Okay, so first of all, we have to assume whether we are expanding or decreasing the size of the loop. Let's say that this thing is the loop area is expanding. Okay, so again, loop area would be this. So if the loop area is expanding, in other words, if delta A is positive, then the flux is increasing. Because remember, flux is B times change in area. And, you know, if you increase the magnetic field or increase the area, you're going to increase the flux. The big new idea here is that an induced magnetic field is created and it opposes the change in flux. So as we pull here, as we pull on this resistor, we have to do work. And in order for us to have to do work, the magnetic field created by the induced current must oppose the existing external magnetic field. So I have the existing external B field as dots there. So now what I'm saying is this loop, I'll do this in red, this loop, there's going to be a current in it, and the magnetic field caused by this current in the red loop is going to have to go in the opposite direction. Okay. So now what I'm going to do is use a right-hand rule to figure out which way that current needs to be. So this induced current is going into the page, and if I think about these loops of magnetic field caused by a current carrying wire, they would have to go into the page on the interior. And if I wrap my hand around that wire, the current would go clockwise. All right. That was a big